Hi there. I will continue doing the questions from yesterday. I got to question three. I've had a look at it, but I couldn't quite manage to complete it. Um, but yeah, so consider a circle with center 0, c, which is tangent to y is equal to x squared. Find the radius of the circle in terms of c. So the important thing to note is that we want r, which will be my radius, in terms of c. Okay, so I think sketch might actually help. That's the first thing I'm going to do. Um, It's my x-axis and this is my y-axis. It is a completely normal parabola, and which goes through the origin. The graph might not actually indicate that well, so I'm just going to shift it slightly down. There you go. And this is y is equal to x squared. Now, the question doesn't actually define what it means to be tangent to the y is equal to x squared curve. So, for instance, you could mean a circle like this, which is like the most obvious thought. But also, something else that could be the case is let me just copy this down here. Is a graph that looks more like this. So let's say like this, which is tangent at the origin, or alternatively, a circle that is tangent to the parabola but on the other side. And because the question doesn't that doesn't specify whether c has to be a positive or a negative number, all of these are possible circles that are tangent to the curve y equals to x squared. Now if I am to denote the center, so let me think of, actually this is probably the simpler case. So this is 0c, and the radius here is going to be r, which is also equal to c. So when the circle is tangent only at one point, the radius is going to be equal to c. If this is the case, if the gray circle is the circle that we're looking at, these will be um, my my center, and this will be my radius. And even in this case, r is equal to c. Now, the more complicated case is when the circle is tangent to the parabola at 2 points. So if I denote the center of it 0c, and then I draw two lines from the center to the parabola, because these are tangents, they make a right angle triangle. And I think it would be actually quite helpful to actually draw the tangents at that point specifically. And to be more specific or pedantic with my working, I should denote this point as, let's say, p squared. And actually, that might be a good thing to do, because now I can first, I know that the general formula for this circle is going to be x squared plus y minus c squared is equal to r squared. I can plug in this point here because I know it's satisfied, it lies on the graph. It's going to be p squared plus p minus c squared is equal to r squared. Now, the only thing I have left, sorry, p squared. Now, the only thing I have left to do is to write P in terms of R. And I guess the helpful thing to notice is that, um, well, yeah, so the radius here is perpendicular to the tangent, which means that the gradients are equal to the product of the gradients are equal to -1. The gradient of this line here, let's say, let me call this O big P. So gradient of OP, so I'm going to denote it like that, is going to be rise over run. So P and C minus P squared. I believe that's correct, yes. And the gradient of this line here, I mean, it's just going to be the derivative of x squared and the point P at that point. So it's going to be y equal to 2a, 2p, sorry. So what this means is that I go down, I'm going to rewrite what we know so far. So we know that p squared plus p squared minus c to the squared is equal to r squared. That's my equation 1. And my equation 2 is that 2p times c minus p squared over p is equal to -1. Um, if I look at equation 2, I can simplify this much more. I know the p's cancel out. C minus p squared is equal to a half, which means that um, c minus a half is equal to p squared. Therefore, p is equal to square root of c minus a half, which means that actually c must have in this case specifically, must have a radius larger than a half, because if that wasn't the case, then we would have a complex number, because whatever is under my square root is negative. So I know this constraint must be the case. So and also um, my circle can't be at the origin, so this is what must happen. Now I'm going to call this equation 3, and I'm going to combine equation 1 and 3 by plugging in this substitution, and I get c minus a half plus c minus a half minus c all squared is equal to r squared. Now this, I believe, simplifies very nicely to c minus a half plus a quarter equal to r is equal to r squared. C minus a quarter is equal to r squared, and therefore r in this case is equal to c minus a quarter. And I believe that should be correct, because it follows on correctly. So there are 3 cases, depending on how you interpret the question. In an actual interview, I'd probably ask my interviewer if the other 2 cases are valid cases. But yeah, this is a pretty straightforward, nice question, not too complicated. Um, I'm checking my algebra here that it's not incorrect. It shouldn't be incorrect. Yeah, it's incorrect. Okay, so this was question 3. Not too bad compared to the first 2, which were, in my opinion, a bit more heavier in the critical thinking. This is kind of a trivial question. Now, question 4. Find the last 2 digits of 1 factorial plus 2 factorial plus 3 factorial plus all the way to 2223 factorial. I think it might be helpful to write down some of the factorials. So 1 factorial is 1, 2 factorial is 2, um, 3 factorial is 6, 4 factorial is 24, 5 factorial is 120, 6 factorial is 720, 7 factorial, I can work that out very quickly, is 5040. And I think I can stop here just for a second. Yeah, so I think it's very important to note that for a factorial number, let's say n factorial, which is equal to n times n minus 1 times n minus 2 times n minus 3 and so on, all the way until 2 times 1. If the number contains, if n contains fives and twos, they combine into tens. What this means is that you are adding a 0 at the end of whatever number you're having because you're multiplying by 10. And we can see this in the 5 factorial example. So we can see that all the factorial numbers from 1 to 4 do not have a 0 at the unit digits, but 5 and 6 and 7 do. And I assume that when we get to 10, you will have 2 zeros, and I think that's very important because we are looking at the last 2 digits. So, and also if we have to work out the last digits of any number, then we are looking at that number modulo 100. So 8 factorial, that shouldn't be too hard to work out. I don't even have to work out all the digits of 8 factorial, but it is good practice to do so. It shouldn't take too long. For 40,320, 9 factorial is just that times 9. And it's just this. And I'm not even going to bother work out 10 factorial. I know it's just whatever 9 factorial is times 10, so an extra 0. Now, this is very important because I just said that I am looking at this modulo 100, so I'm going to add up all the last 2 digits of all the numbers I've had so far. So if I have to highlight them, it's going to be, actually this is a very bad highlighting. It's going to be all of this. Actually, I know 11 factorial is going to have 2 zeros at the end. 12 factorial is going to have 2 zeros at the end. 15 factorial is actually going to have 3 zeros at the end, and so on. So I don't have to bother thinking about all the way to 2023. And I do think if this is not a trick you can see for, like at first glance, or not even at first glance, if after 10 minutes you don't see this trick, it's worth revisiting your understanding of factorials. So this is why this is either a very complicated problem or a very easy one. So if I add all of this up, 1 plus 2 plus 6 plus 24 plus 20 plus 20 again plus 40 plus 20 plus 80, and I don't really care about the 10 factorial. This is 33 plus 80 plus 100. This is 121, 111, nope, plus 180 is equal to 213. And this means that the last two digits of 1 factorial plus 2 factorial plus 3 factorial all the way to 2023 factorial is going to be 13, the last two digits. Okay, so this again wasn't a massively complicated problem, but I can see how it's very easy to get stuck. Um, the next question, which I actually don't seem to have on the board, question 5. Just going to screenshot this very quickly. And just to check on time, I have so far spent only 15 minutes and I have done 2 questions. So this is much better than my previous attempts. But it is also true that I have seen these questions from before, so I have had some time to kind of think about it. Question 5 and 6 and 7, I haven't at all. So this is where it's going to become, again, very much not trivial anymore. Consider sequence x n plus 1 is equal to 2x squared minus 1 with x naught equal to a, which is a rational number. Find the values of a for which this sequence is periodic, i.e. there exists integer k and p such that xk is equal to xk plus p. This is a very interesting problem. We're dealing with periodicity of a sequence. Now, every time I see sequences like these, I think the first thing to do, it is perhaps important to enumerate some of these um, terms in the sequence. So I'm going to do just that. So I know x naught is equal to a. X1 therefore must be 2a squared minus 1. And it follows that x2 is going to be x1 squared times 2 minus 1. And it is going to be quite long to work out. But this is a Trinity Cambridge question, so I don't think the algebra should ever be what stops you from getting the question right. This is 8a to the 4 and 8a squared plus 1. Okay, I don't see a obvious factorization to this. I do notice that 8, 8, 1 are quite nice numbers. It may not actually factorize to something. I'm going to keep it that way for now. I'm going to move on to x3, which is equal to 2. I might have to speed up here. This might be very boring. I actually can't do this in my head. Bear in mind it's almost midnight, so my maths is rubbish, and I am on half a brain cell that is barely working. 64a to the 8 plus 64a to the 6 plus 8a4 plus 64a to the 4. No, 6. 64a to the 4 plus 8a squared. And then it's going to be the last terms are just plus 8a4 plus 8a squared plus 1 minus 1. This cancels out. Actually, no, it doesn't, because this is inside a bracket. Now I have to simplify this. How many a to the 8 terms, or just one? How many 64 to the a to the 6? I have one, two of those, that's 128 in total. How many to the 4 of them I have? That's one, two, and three. So this is 16 plus 64, which is 80. I'm just going to check. 74 plus 6, 80. Yes, that's correct. And lastly, 16a squared is 1 minus 1. Okay, that should be everything. Now I'm going to tidy this up. It's going to be 128 a to the 8 plus 256 a to the 6. I should have not picked a. I mean, I didn't get to pick a. The question stated a. 160 a to the 4 plus 32 a squared. And this is just going to be 1 plus 1 because 2 minus 1 is 1. Okay, so I have generated a few terms. And I can't notice anything important. Well, I know that a can be written, so I think it's very important to note that a can be written as, let's say, alpha over beta. Of course, beta is, well, actually, doesn't have to be. Well, beta isn't 0. What else can we say? For this to be periodic, one thing you can think of is alternating signs. So, for instance, 1 minus 1, 1 minus 1 is a periodic sequence, but I'm not quite sure how you can relate this to the problem. Okay, there is some thinking that needs to be done. I'm not going to continue working out more um, terms to this sequence because it is quite algebraically heavy. It's very likely I make a mistake. If I make a mistake early on, I will have the whole thing wrong. So I will keep it from the x naught to x3. That's 4 terms. That's more than enough, hopefully. I can't spot a pattern. Um, but I want to see if I can find some general terms. So if I have xk, is there a way I can write some general formula to this? Well, there is going to be k, sorry, 2 to the k amount of terms. So, for instance, this would satisfy x naught, but for instance, if we are to plug in x to the 1, x1, we will get 2a. So this is clearly not correct. So perhaps we need to add something more. I'm going to kind of try to build this up by inspection, if even it exists, such formula. A squared, so a, what could work? There is always, there's a minus 1, plus 1, and plus 1. And I think you're always going to have a plus 1 after your x1 term, which is helpful to know. Interesting. Um, The very annoying thing about this is that I don't really have a way to get hints. So this is just kind of me staring at this until I get it right. Perhaps I can consider. Um, I think I should go by inspection, try to work out what happens. Um, for instance, 2k a minus 1 squared minus 1. This is equal to a squared. Actually, this is not never going to work. Perhaps if I did this, 2k a minus 1 k minus 1. This is also not going to work. I don't think this is the way to do it. I need to reread the question. Values of a for which the sequence is periodic. Okay, perhaps I can choose some a. Well, one is one irrational number. Technically, it is. Let me try a half. Okay, x equals to a half. Let me try that. So I'm gonna go down here and I'm gonna try that out. So x naught is equal to x naught is equal to half. Means that x1 is equal to 2, 1 plus 1 over 2 squared minus 1, which is just a half. This is a half minus 1, which is minus a half. X to the 2 is 2 minus a half squared minus 1. And this is going to be, again, a quarter times 2, half minus 1 minus a half. X to the 3 is going to be 2 minus, it's going to always be minus a half. So you can say that this sequence is periodic from x to the 1, and it's like the same every time. So perhaps this might be my limiting term. That I mean that this is the term that's constant in that sense. Let me try. X is equal to x naught is equal to. Let me think of a different fraction. A quarter. So x1 is equal to 2 1 over 4 squared minus 1. This is equal to a 16th and an 8 minus 1, which is equal to minus 7 over 8. Is that correct? Yes. X to x2 is equal to 2 minus 7 over 8 squared minus 1, which is equal to, that should be correct, 64, 32. So 49 over 32 minus 1, which is 49 minus 32 over 32. And that equals to 17 over 32. Now, I do not think this is going to be periodic at all. Okay, so I'm going to try a different number. And until I have an epiphany, I'm going to have to try different values. So x naught equals a third. X1 is 2 a third squared minus 1, which is just 2 over 9 minus 1, which is 7 over 9. 7 keeps on appearing, is quite annoying. This is equal to 49 times 2, which is 98 over 81 minus 81. So 9 plus 8 is 17 over 81. Actually, this pattern keeps on repeating. 17 is there too. Perhaps let me try a different um, x naught. X naught fifth. This one is going to be 2 over 15 and 2 over 25 minus 1, which is equal to 2 minus 25, which is minus 23 over 25. Okay, let me try a whole number because x naught can be a whole number. Although I think the question's phrasing specifically that it can be a rational number might be a big hint. Yeah, because 2 times 1 minus 1 is always going to be 1. Okay, so this is very similar to what happened to the half. Let me try this. This is going to be 4 plus 2, 8 minus 1, 7. So 2. 49 times 2, 98 minus 1, 97. And this is very much increasing. Okay, so 2x squared minus 1, as I'm going to take the limit of this, as it tends to infinity, is also going to be infinity. That means that for you to have a periodic sequence, you must have x to be less, the modulus of less than 1. If you count 1, 1, 1, 1, 1, 1 as being a periodic sequence, then actually 1 is included. So that's very important. So that's some progress in this question. Right now, I am going off assumptions. I am not exactly doing. I haven't put much thought into this question beforehand, so I'm completely in a new area. So from the few examples, I think it's very important to note that the example x naught equals a half is very interesting. A quarter is also interesting if you compare it to a third. But I do think I should see what happens with numbers that are larger than a half but less than 1. So x naught is equal to what's larger than a half, less than 1. Let's say 3 over 2. No, that's more than 1. Sorry. 3 over 4. This is going to be 18 over 16 minus 1. And this is 9 over 8. 9 over 8. 64 minus 32. This is going to be a negative number, minus 31 over 32. I am not quite sure this has a period. But you can kind of quickly see that this is just 2 over 16, this expression here, which simply passes 1/8. So no. Well, I can't really establish just from these few calculations that actually this is not periodic. It might very much turn out to be so. What if x naught is equals to, what's another very nice fraction? Um, 2/3, 2/3, yeah, which is more than a half. So it would be 8 minus 9, so minus 1/9. And how do I know this is going to be periodic? Because this is going to be very long and not very helpful. Yeah, this is just very hard to work out. Perhaps I might need a hint. Okay, I'm gonna ask Google to give me a hint with this question, but not solve it. I prefer this. Give me a hint, don't solve it. Let's see if it works. A good approach is to use a trigonometric substitution to simplify the recurrence relation. Consider the double angle identity for cosine. Try letting xn equal to cos theta n and see how the recurrence transforms. This will give you a new recurrence for theta n. Think about what periodicity for the sequence xn means in terms of a new sequence xn. Remember to also consider the constraint that x theta is equal to a, x not equal to a must be a rational number. Okay, that's interesting. So if I go back here, so essentially what I'm asked, I'm actually going to copy this into there. It might be a very, it's very good. I was thinking of cosine and sine theta. I just didn't think this is something I could do. Yeah, that's my hint. Okay, nice. So my reoccurrence relation x plus 1 is equal to 2x squared minus 1. This is n. Um, Double angle identity for cosine, they're actually like a bunch. It's like cos squared theta minus sine squared theta, or 1 minus 2 sine squared theta, or 2 cos squared theta minus 1. So these are all the ones I can remember right now. Oh yes, so this one matches the format of this. So if I let xn equal to cos theta, then uh, cos theta n plus 1 is equal to 2 cos squared theta minus 1, which is just cos 2 theta n. So cos theta n plus 1 is equal to this. That's very interesting. Okay. That's a massive hint. That's a very helpful. So I know that say theta if theta is equal to, let's say, pi, then cosine repeats every 2 pi, k, where k is a real number. Actually, it's integer, including 0. So, cos pi, cos 2 pi, cos 4 pi, cos 6 pi, and so on. What I am perplexed now is what can I do with this information? Well, if I can I write this in terms of, so that means that theta is equal to r cos xn. Just substitute that back in there. I have okay. That's interesting. Um, is there a way I can do this? Is there a way I can simplify cos with argument to r cos theta n? Is there a way I can do this? Um, I don't think so. I mean, this is x, not. So that might actually be enough because if x naught is equal to, let's say, um, let's say pi by 3, then x1 is equal to cos 2 half, which is just cos 1, which doesn't make sense. Um, okay, what if I say that I want this to be equal to a specific angle, like pi by 6, or yeah, actually 3 is better. Cos pi by 6 is root 3 over 2. So actually, if I say, if I start with what? If I say that x naught Well, root 3 over 2, root 3 is a rational number. So this is not in Q. So this might be very much pointless. Well, so what other values can I make these equal to? I can say 2 cos minus 1 xn equal to, let's say, pi. That means xn must be 0. I don't like this. Say, if I have pi by 4, then I have root 2 over 2, which is also irrational. Root 2 is irrational. The other value I can have if I have pi by 2 here. No, not pi by 2. 2 pi. Then xn would be cos pi, which is minus 1. Okay. So if x naught is minus 1, then x1 is equal to remember this correctly, cos 2 cos minus 1. So on our cos minus 1 is our cos minus 1, I just said it, is pi. This is 2 pi. Cos 2 pi is 1. So x2 is equal to cos 2 cos inverse of 1, which is cos, again, that can be 0 or 2 pi, it doesn't matter. So 2 pi, or 4 pi actually, this is still 1. Okay, so this is periodic, this works. It has a period after a certain point, but it still works. Okay, I would say I am done with this question. I will do more thinking about this later on. But yeah, I would argue that this is going to be my limit for this question. Yeah, I guess that's pretty much all the cases you can consider. Let me see what the next questions see and how much time I've spent doing this. It's almost an hour, so perhaps starting new questions might not be nice. Perhaps questions I've done before, just to refresh them. But yeah, no, I think this is more than sufficient for today. I have done a lot of these questions. But yeah, this is more than enough for today.